Imagine if I did.
So we've got a few reactions left to do. We've got some practice problems here, and we have some mechanisms. And I really want to prioritize the mechanisms because I can always post answer keys for the practice problems. But I want to start by covering the reactions that we were doing. We were dealing with these crossed aldols. Can you remind me what an aldol reaction entails? Actually, rather than asking you to remind me, I think I'll clarify. This unit is covering reactions just with aldehydes, ketones, and esters, and the carbonyl carbons of those groups. Aldol reactions are those addition or condensation reactions that include aldehydes or ketones. So it's not all, that's a weird way of writing it actually. It's not all carbonyls that go through aldol reactions. It's just aldehyde and ketones. And in the examples that we showed, the aldol reactions took two equivalences of our carbonyl and did acyl addition to the beta hydroxycarbonyl, or did elimination, the condensation reaction gave us the conjugated carbonyl. So if you take two equivalences, that's the aldol. What is the distinction then about the crossed aldol? What distinguishes that from just a regular aldol reaction?
A ketone attacking an aldehyde, and then it can switch to like a ketone attacking a ketone.
Having two different carbonyl structures. So rather than taking one compound and hoping that half of it acts as the nucleophile while the other half acts as an electrophile, the crossed aldol reaction is when two different carbonyls. So it could be this example that a ketone is a nucleophile to an electrophile aldehyde. It could be that the ketone is a nucleophile to an electrophilic ketone. The idea that you have two different compounds that could both be the nucleophile or the electrophile. So we said we can limit crossed aldol impurities. We can limit the mixture of products that we get. We can do that by limiting alpha hydrogens. How did this improve our ability to limit the mixed products? It minimized how many nucleophiles are possible. In the crossed example, both acetone and acetaldehyde could be the nucleophile. But now in this first example, only cyclohexanone can be the nucleophile. Tert-butyl ketone can't be a nucleophile. I said minimum nucleophiles, but I think another way of saying that is that it limits the nucleophiles. The other way that we saw, though, that actually cyclohexanone being the only nucleophile doesn't mean that it's not also the only electrophile, or that it's not an electrophile. So what I showed yesterday was there is still an additional mixture product where cyclohexanone reacts with cyclohexanone. So the other way to improve this is to promote reactivity, meaning have one electrophile that is more reactive, a more reactive electrophile. This makes it more likely that your nucleophile forms or will always attack this specific electrophile. Now, I think the problem with the example that I gave is really it would be best if it contributed to rule number one as well. So the modification that I would give, or I'll just clarify, here is the combination that I showed, which highlights promoting reactivity because aldehydes are more electrophilic than ketones. But there is still the chance of this aldehyde becoming a nucleophile. There's still a chance of this ketone becoming a nucleophile. So really a better way to promote reactivity let's limit alpha hydrogens, which means that this aldehyde can never be the nucleophile, and promote reactivity, meaning that this ketone is less likely to be the electrophile because there's a more reactive electrophile. There is still the chance that you get a mixture. There's still a chance that you get a product where ketone attacks ketone, or alpha carbon of a ketone attacks the carbonyl of another ketone. But because the aldehyde is more reactive, it pushes us in the direction. These are nice rules, but in organic synthesis, sometimes you don't have the freedom of just modifying your carbon chain however you want. Sometimes in organic synthesis, you need a specific carbon chain, and you can't really lean into these. So by far, the most effective way to control the products of a cross-aldol reaction is the use of complete enolization. If you have a carbonyl that you want to be the nucleophile, and you don't want it to attack itself, you don't want it to do this typical aldol reaction, then just turn it into a nucleophile. The problem with using a base like hydroxide or even a small alkoxide is that this enolate that we make is only 10% of the solution. Even when we use something like tert butoxide and we get the kinetic enolate, meaning the less substituted alkene, even tert butoxide, because we're working with an alcohol in the conjugate acid, our equilibrium is split and it favors too heavily the reactant, which means I have 100 molecules of what I want to be the nucleophile, and only 10 of those molecules are becoming nucleophiles, which means there's still 90 electrophilic versions that might run through these crossed issues. So what do we use for complete enolization? We use LDA. And it's true that LDA is still a kinetic base. So if there is regiochemistry, like on this ketone, it still chooses the least substituted side. Aldehydes and esters don't have that regiochemistry issue. But this gives 100% enolization, which means in a solution with itself, there is no electrophilic component left. Can't get a mixture of products. So then how do we show that? All right, well, in this last example, I'm actually flipping the table. I'm introducing a ketone, which is a less reactive carbonyl. And both of my carbonyls, cyclohexanone and this propanaldehyde, I don't know why I'm saying it that way, propanal, they both have alpha hydrogens. So I want you to recognize that this last example, it doesn't follow the first two rules. It doesn't limit alpha hydrogens, and it doesn't promote reactivity. That's the point of complete enolization, is if I can't lean into these two rules or into these two methods, complete enolization allows me to get around that. The thing that I'm struggling with in presenting these reactions, though, is the way that the reagents would need to be said. I think there's some truth here that we should follow this reaction with hydroxide. You'll notice that the aldol condensations themselves, they do work well with hydroxide as a base. LDA, on the other hand, hydroxide catalyzes the condensation, but LDA does not catalyze. So we would still need some sort of base in these steps to be able to work this up. So what does this make? after LDA is introduced, the LDA reacts with the alpha hydrogen and produces my enolate. After the enolate is introduced to an electrophile, it goes through acyl addition. So this is the product that actually forms after step 2. The alpha carbon has attacked a carbonyl carbon. The alpha carbon, or the beta carbon, was a carbonyl carbon. The beta carbon is now beta because it's no longer a carbonyl and because it has been attacked by alpha. And it's that hydroxide step that actually helps to promote the rest of the process where the final product is formed. We're going to look at this mechanism. We're not going to look at the mechanism with LDA, but we are going to look at the mechanism for condensation, and that should help clarify why hydroxide is needed after LDA. Questions about the aldol condensation, aldol addition, or the crossed aldol? Since you have no questions, then what I want to demonstrate is there is another way to show this. What if you're doing a road map and it looks a little bit different? What if it wants you to create a carbonyl? This is essentially the process we're looking at up top, forming that same product. What if it wants you to make a carbonyl and then use that carbonyl as the electrophile? How do I know that's the electrophile? Because it becomes the beta carbon. Alpha attacks beta. And here is beta, so beta must have been attacked. This route says, I have my nucleophile, let me introduce it to LDA and then the electrophile. This route is saying, I have my electrophile, I want to introduce it to a nucleophile. Well, that means I'm not going to introduce these as 2 steps. I actually want them to come together. So I could show this one of 2 ways. I could quite literally just show the electrophile, I could just show the nucleophile that I want. And just recognize that these are resonance forms of each other. So neither form is more appropriate or inappropriate to show if you are saying this is the reagent I want. You could also approach this, though, by saying, I can't find this in a lab. No one's going to sell me this enolate in a bottle. So I can make this enolate by introducing my carbonyl with LDA. So just by writing out those 2 things, if you have a mixture of this carbonyl and LDA, no, you don't. It's like saying if I have a mixture of hydroxide and hydronium, I go into the lab and I drum up a mixture of hydroxide and hydronium. If I have a mixture of hydroxide and hydronium, no, I don't. If I have a mixture of these 2 things, they've already reacted. So if I say I've got a carbonyl and LDA, no, I don't. I have an enolate because that's how they react together. But you have to mix them together at some point to make that enolate. Both versions are good. Both versions are accurate. All right, moving on to the Claisen, Dykman, and crossed Claisen reactions. If the aldol reaction involves aldehydes and ketones. The Claisen reaction involves esters. Also recognize that there is no Claisen addition like there was aldol addition. There's only Claisen condensation, and there's a good reason for that. The distinction between a true Claisen reaction, I'm not saying that because it's commonly said, but I'm going to clarify why others are basically Claisen condensations. A true Claisen condensation just takes two equivalences of an ester, and if you want to, you could show that as those two separate equivalences. What functional group is formed there by the Claisen condensation? It's one of the new functional groups I want you to be able to identify. Good. Beta keto ester. What you can see is that the alpha carbon of one carbonyl attacks the carbonyl carbon of another carbonyl, which becomes the beta carbon. Once again, alpha is nucleophilic, beta is a carbonyl carbon. Alpha attacks beta. What happens in this process is that alpha actually substitutes the OR group. What is being condensed out of this structure? In the aldol condensation, the reaction condenses two hydrogens and an oxygen. Dihydrogen monoxide. I told it to my Ochem 1 class and they really got a kick out of it. Aldol condensation condenses water. Claisen condensation condenses an alcohol. This OR group gets lost, and one of these alpha hydrogens gets lost. So this condenses out an alcohol. All right, pretty simple. Claisen condensation. It still needs a base to run, but instead of using hydroxide, because hydroxide will saponify the ester, this simply requires a base that matches the ester linkage. If it's a methyl ester, we need meth oxide. Ethyl ester, eth oxide, so on. All right, and then we have this intramolecular Claisen condensation, which is called a Dykman condensation, which I think is a shame because it should just be called the Claisen condensation intramolecular. Because it's intramolecular, all we have to notice is that there are two esters within the structure, and the alpha carbon, I don't really like how I simplified that. The alpha carbon of one attacks the carbonyl carbon of the other. One of these carbons will be the nucleophilic alpha. One of the carbonyls will be the electrophilic beta. We still use whatever base matches their ester linkage, and we still get a beta keto ester, but this time because it's been done intramolecularly, we get a ring that forms. So we get some cyclic beta keto ester. And I apologize to Dykman if I spelled his name wrong. It should be called the ester condensation reaction anyways, so. Okay, and just like aldol reactions, we have crossed Claisen reactions, meaning we have the potential to take one ester and have it attack a different ester. So when doing these Claisen reactions, equilibrium is producing a very small amount of nucleophile and leaving a large amount of electrophile. And so equilibrium is slowly producing nucleophile to do the reaction. That's if I introduce an ester and that weak base, I'm always going to have some mixture with itself. So how do we avoid having those crossed products? Use complete enolization. Take the ester that you want to have as the nucleophile and introduce it to LDA. Okay, I've made a small oversight I want to clarify. The true Claisen reaction has two steps. First, basic conditions, then acidic workup. The Dykman condensation, first basic conditions, then an aqueous workup. And even the crossed Claisen, if you first use LDA and then you introduce your ester, you still have to do an acid workup. So I want to talk to you guys about why we need to do that acid workup. We did not have to do that acid workup with aldol condensations, but we need an acid workup with Claisen condensations. The Claisen condensations are catalyzed by this base, a lot like how aldol condensation is catalyzed by hydroxide. So that means the alkoxide is deprotonating the ester, and then it's being reformed by the time the beta keto ester is produced. What's more acidic, the alpha carbon of an ester or the alpha carbon of beta keto ester? So here's that RO minus reacts with our ester, makes an enolate. Then our enolate attacks another ester, makes the beta keto carbonyl, and makes a new equivalence of our base. What's more acidic, the alpha carbon of the ester or the alpha carbon of the beta keto ester? And the reasoning? It's not because of substitution, although that does change. There's something more that impacts it than just substitution. It's not the induction either. It would be induction if we compared the alpha carbon of the ester to the alpha carbon of the ketone on the left, but the shared alpha position is more acidic, and the reasoning is? You've named two of the reasons, so it's the third reason. It has more resonance. This alpha carbon is in resonance with the carbonyl, but this alpha carbon is in resonance with both carbonyls. So if my base was strong enough to form an enolate with the ester, is my base strong enough to form an enolate with the beta ketoester? Absolutely. In fact, it's more likely that the base reacts with my beta keto ester than it did with my original ester. So by the time you've finished a Claisen condensation, you are not left with a beta keto ester. At the end of the Claisen condensation, you're left with an enolate. So to isolate the beta keto ester, we have to add this aqueous workup. If you notice, it is one step backwards, one step forward. Or one step forward, one step back. I've had students that approach this and they say, I'm done. I've got my product. I don't know why I have to show this extra step. The reason you have to show the extra step is because for the first step to work at all implies that this deprotonation step definitely works. It has to happen. It does happen, so it has to be worked up. All right. Again, we're going to go through some mechanisms, but the last thing that I want to introduce here in terms of these reactions are other types of crossed reactions. I've not found any names for these, and I don't know exactly how to name them, so I've just called them crossed condensation. Since we know aldol condensation applies to aldehydes and ketones, Claisen condensation applies to esters, then these are not aldol because they're going to include both esters and aldehydes or ketones. So they're not aldol, they're not Claisen, they're a little bit of both. If you look on the examples that I've given, we can show things. Okay, we've already shown things like aldol gives us beta hydroxy aldehyde or ketone. Aldol gives us alpha beta unsaturated aldehyde or ketone. Those are the hallmarks of the aldol reactions. The Claisen reaction gives us a beta keto ester. These crossed reactions will give us things like beta hydroxy ester, meaning the ester was the nucleophile to an aldehyde or ketone. That's the new component here. It's not aldehyde attacks aldehyde, it's not ketone attacks ketone, it's not even ketone attacks aldehyde or vice versa. It's not Claisen, it's not ester attacks ester. Now it's ester attacks aldehyde or ketone. Same thing for the alpha beta unsaturated ester. It means that the ester served as a nucleophile to the aldehyde or ketone. And the last type that we could make is a beta keto aldehyde or ketone, which implies that the aldehyde or ketone was a nucleophile to an ester. If Claisen condensation makes a beta keto ester, what type of condensation makes a beta keto ketone, not Claisen, because Claisen makes an ester. So it's a kind of a combination. What do you notice about those crossed reactions that are presented? Oh, I messed up on my sheet. You guys notice on the top Claisen example? It starts with ethyl acetate and it ends with methyl acetoacetate. That should be an ethyl ester in the product. What do you notice about even the crossed Claisen that's presented as the third reaction, and then the crossed condensations, not to mention looking back at the crossed aldol and the best way that we did crossed aldol? What do they all have in common? They all start by using LDA. They all leverage complete enolization because I don't want to risk having these mixtures produced where a nucleophile accidentally serves as an electrophile. So they all use LDA, which controls what reagent serves as the nucleophile and controls which reagent serves as an electrophile. I'm just going to say it one more time. Aldol reactions have aldehydes and ketones as both nucleophile and electrophile. Claisen reactions have ester as both nucleophile and electrophile. It's these other crossed reactions where we can have an ester be a nucleophile to an aldehyde or ketone, or we can have an aldehyde or ketone be a nucleophile to an ester. You know, when I got into OChem 2, I thought I never heard the word nucleophile again. I don't know if maybe I wasn't listening for it, or if maybe my professor didn't say it that often. But I remember thinking back on my OChem 1 experience and thinking, why did they shove that word down my throat so much? Why did it matter that I knew what a nucleophile was? From teaching OChem 2, I see it. Everything has a nucleophile or an electrophile. Being able to identify what serves as what is super useful. Okay, I have a retrosynthesis problem. In order to help you solve the retrosynthesis, I want to demonstrate the retrosynthesis of some of the structures that are already just presented in our reactions. So taking from the front side, I'm taking this aldol condensation product, and I want to retrosynthesize it. So I'm actually going to have an arrow that says this came from whatever the arrow is pointing to. Here's what I'm going to do. I'm going to start by labeling alpha and beta. Might there be more than one beta? Yes. Might there be more than one alpha? Yes. So how do I know which alpha and beta I'm looking for? I'm looking for my functional groups. I'm looking for a beta hydroxycarbonyl, and I'm looking for that beta carbon to be labeled as beta. I'm looking for an alpha beta unsaturated carbonyl. I'm going to label those as alpha beta. Hey, I've got that. Alpha beta unsaturated carbonyl. Step 2, beta was an electrophilic carbonyl. Alpha was a nucleophile. That's actually not even a step. That's just a reference. We need to cleave the alpha-beta bond because alpha was a nucleophile that attacked beta. So step 3, cleave alpha-beta bond and make sure that beta is a carbonyl. All right, so here I go. Alpha, beta have that double bond, so I'm gonna cleave it. You know what? I'm gonna model this by actually re-sketching it and then cleaving the bond. Alpha was the nucleophile. Beta was a carbonyl, so I will place an oxygen back on that beta carbon. Now it's a carbonyl again. But this doesn't really tell me how they formed. It doesn't clarify the nucleophilic character. So if I wanted to show this synthesis, I would say first introduce my nucleophile with LDA, then introduce my electrophile and have that catalyst added, the hydroxide, to force it forward. It's a crossed reaction, so I want to be able to produce a nucleophile before I introduce the electrophile. This is how I want you to tackle these retrosyntheses. First, introduce the nucleophile, because then you'll work with LDA. Then introduce the electrophile. And I've given you the reactions already say 1, 2, 3. This is what you could do on the side if you wanted to just try breaking it apart. Do you guys want a minute to solve those, or do you want to keep pushing? Let's keep pushing. Okay. Okay, actually, we have the chance to pause here and look at the aldol condensation and the Claisen condensation mechanisms. Or we can look at the last few reactions and then come back to wrap up with the mechanisms. Shall we do the mechanisms now? We've looked at these reactions. So now is the time to predict their mechanisms. Which one has more steps? Aldol condensation or Claisen condensation? Neither. Thank you. They have the same number of steps, which is great. Let's start with the aldol condensation. What reagent can I use over the reaction arrow to make this reaction happen? What reagent can I provide?
A thermal base?
One more time.
Is it like a thermal base? Because you have the most sub.
Well said. I need a thermodynamic base to give me the thermodynamic enolate, to give me the alpha-beta unsaturated structure on the right. This is something students have complained about in the past. I sometimes forget about it. We could say 2 equivalences of this carbonyl is needed. It wouldn't matter because how do I get double that? Well, I just take whatever I have and I cut it in half, and now I have twice as much of it. So sometimes you'll see this. I try to make sure that you see it. So Justice, you want to suggest a thermo base, a thermodynamic base? Hydroxide is great. All right. Step 1, formation of the enolate. Consider, are you in acidic conditions or basic? Good. I'm not going to protonate anything. in basic conditions, I have to consider, will the reaction, does the reaction have an acid? Should I do acid-base chemistry? Or does the reactant have an electrophile that I can do electrophilic chemistry? Actually, it has both. This reactant has an acidic alpha hydrogen, but it also has an electrophilic carbonyl. We know what happens if hydroxide does acyl addition. It doesn't do anything that helps us form a nucleophilic alpha. Just because it can doesn't mean we want to show it here. All right, well, I'm going to draw out one of my alpha hydrogens because it's going to be involved in this step. I prefer to show the most stable form of the enolate. Oh, you know what? I'm going to draw both equivalences of my carbonyl. It's just that only one equivalence is relevant right now. I like to show the major resonance form, but I have seen students that are confused about why that resonance form attacks from the alpha carbon. Isn't it a negatively charged oxygen? Why would carbon attack? Carbon shares electrons more willingly. Carbon holds those electrons just as much as oxygen. So you can draw the other resonance form if you want to. I happen to like this. Then we have acyl addition. I wrote this as nucleophilic attack. I might recommend just calling it acyl addition. That's exactly what it is. And we've seen acyl addition a number of times this semester. So we know the process of acyl addition. Here, the nucleophile comes from the alpha carbon, which requires that my enolate reforms the carbonyl in order to attack from the alpha carbon. Alpha attacks a carbonyl. Guess what? That carbonyl is now beta, because when alpha bonds to something, that something becomes beta. In this protonation step, we are forming the beta hydroxy carbonyl. We've just done acyl addition, so we have a negatively charged oxygen, and our catalyst has not been reformed yet. So our alkoxide acts as a base, protonates the alcohol, and regenerates our hydroxide. Nice. You've just shown the mechanism for aldol addition. How hard was that? Not very hard. A little interesting, a bit unintuitive sometimes that one equivalence becomes a nucleophile and one equivalence remains an electrophile. If we wanted to stop at the aldol condensation, we're done. But if we want to show if we want to stop at the aldol addition, we're done. If we want to show the condensation, we have another step to go. Our base has just reformed, and I still have an acidic alpha hydrogen that can reform another enolate. The formation of the enolate is important here. It tells us that that negative charge is stabilized by the oxygen. It reminds us carbon itself is not very acidic, but carbon that can share in resonance is more acidic. How many enolates form in this mechanism? 2. The first step is an enolate, and the second to last step is an enolate. But this enolate will not attack an electrophile. This enolate instead goes through elimination, and what it kicks off is perhaps the strangest thing that we've seen. It kicks off a hydroxide. Carbonyl reforms. The enolate shifts its pi bond to become the alpha-beta unsaturated pi bond, while the OH group is kicked off as OH minus. We condensed a molecule of water, and we recycled our catalyst. Easy? The biggest mistake that I see students fall into here, they'll skip one of these steps. They'll kind of combine enolation. I don't remember writing that, and I didn't mean to call it that. I just meant to. Enolation's not a bad word, actually. They'll combine the formation of the enolate with the elimination. See, I wrote eliminate instead of elimination. Anyways, I'll see students that take this alpha hydrogen and directly form the alpha-beta carbonyl while kicking off the hydroxide. I get it. That's not a crazy idea to say, why can't this just happen at once? But it doesn't. That's the important thing. Yes, it could happen, but it doesn't happen. The most plausible mechanism is that first the enolate forms. Then that enolate can do something quite challenging. The enolate can kick off hydroxide. Hydroxide itself is not going to be good at forcing the elimination of another hydroxide, but the enolate is better at forcing that elimination. Questions? Okay, now you guys know that I like intramolecular reactions. So this next mechanism is a lot of drawing just because I wanted you to have to draw. What reagent can I put over the reaction arrow here to make this reaction occur? I could use LDA here, but I also don't need to use LDA. This is a Deichmann condensation, but it also feels a little bit like a crossed Claisen condensation. The reason I say it's Deichmann is because it's intramolecular. The reason I say it feels like a crossed reaction is because I have two different esters. Those esters have different carbon chains coming off of their carbonyl side. But I've already limited alpha positions There's only one alpha hydrogen available, which means that I've also promoted reactivity. I've got one carbon that is nucleophilic, one carbon that is electrophilic. I could show this with LDA. I could also show this with a thermodynamic base. What base could I use if I was going to use something small? And not could, should. What base should I use?
NaOCH3.
Good. You know a name for that?
Sodium methoxide.
Good. We want methoxide. And do you need to show the sodium? No, not really. Because it's a counter ion, it's not going to actually play a role here. First, sodium, or as you said, we could do LDA. Then, the aqueous workup. Step 1, deprotonation. Form the enolate. Great, we get to draw it all over again. I'm going to draw out one of my alpha hydrogens. I always want you guys to feel comfortable with all the different ways that you can abbreviate a structure. So we've got methyl esters drawn in bond line. We've got methoxide drawn with chemical formula. We've got methoxide drawn with its IUPAC abbreviation. Nothing changes here in that first step. We just form the enolate. It just happens that this time the enolate is an ester enolate. This gives me a molecule of methanol. That molecule of methanol is the molecule of methanol that gets condensed out of this reaction. Once again, I called it nucleophilic addition, a nucleophilic attack. My mistake. Better to call it acyl addition because I want you to remember how many times this semester you have attacked a carbonyl and opened that carbonyl. This attack comes from the alpha carbon because that is the nucleophilic spot. Do you know what's kind of fun about arrow pushing? It doesn't matter where your arrow is in the middle of the pushing. It just matters where your arrow starts and where your arrow ends. So I've got a weird connection here. I'm actually going to show this pi bond attacking the carbonyl like this. I could have gone down the other way, but it doesn't matter because all I'm saying is alpha attacks beta. All right, now this actually is more challenging. If this is alpha and this is beta, then I've got carbons 3, 4, and 5 connecting them. I know that I'm going to make a 5-membered ring. I've already been given the product structure. But I want to confirm that this is where I make that 5-membered ring. And I can see that. Carbon 1 attacks carbon 2. Alpha attacks carbonyl. Alpha attacks beta. 3, 4, 5 brings us back. Carbon 2 that just got attacked goes through this acyl addition. Oh, a lot like this. When we did acyl addition last time, we also got that negatively charged O. And then carbon 1 has that recently reformed ester coming off of it. Carbon 1 attacked carbon 2, 3, 4, 5, brings us back. Do you know what? We've seen mechanisms a little bit like that throughout this semester. Before the midterm, we learned that esters can be reduced to alcohols, and there's an intermediate that looks a lot like this, where the ester gets opened into an O- and an OR, And in that, an elimination step occurs where the carbonyl reforms and the ester group is lost. We've been looking at a process like that all semester long. I've just created a new equivalence of methoxide. If you're paying attention, that is the catalyst being reformed. Oh, but I have an even more acidic alpha hydrogen than I had earlier, because now my alpha hydrogen is alpha to two different carbonyls. It's in resonance with both of them. So once again, I have another enolate formed. Good morning. So in terms of running this reaction in lab, if you run this whole process, your final structure is this enolate, which, by the way, is not synthetically useless. We actually said that these beta keto groups, we used them in our worksheet yesterday for alpha substitution. So that beta keto enolate, that can be used for something. But if that's not what we want, if we don't want to use it for something, then we introduce a proton. And our most basic position, the alpha position, accepts that proton and gives us our final product. That's both of them, both of the mechanisms. Aldol condensation on the right, Claisen condensation on the, nope, yeah, I don't know my left and right. Aldol condensation on the left, Claisen on the right. Aldol shown step by step, Claisen shown fully sequentially. You know, it's been less than a year since I've started teaching my mechanisms step by step. A year ago, I used to only teach my mechanisms like this, fully sequentially. It takes longer to write them out like this, but it declutters the mechanism. Makes it a lot easier to understand what change is happening, what arrows are going on. And I've noticed an improvement in student comprehension, student comprehension. When I see students actually following step by step rather than just trying to do fully sequentially, it gives you a target. You know exactly how many steps to show. Don't show more, don't show less. You know the names of those steps, so you can make predictions about what is going to happen. I had a student in the fall that came in for the final, and his cheat sheet was only words. There were no structures on his cheat sheet at all. And for mechanisms, he wrote out the definition of what happens at each step. And I later talked with him, and he said maybe that wasn't the way to go about it, but it was an interesting approach. I've never seen it before. All right. Yeah, okay. All right, I want to actually take us back to this page where I showed the Dykman condensation. because there's a bit of nuance that I breezed over. You'll notice that this Deichmann condensation is not a symmetric molecule, and it had a preferred structural isomer product. I want to talk about why that is. If I label my alpha and beta positions, I'm going to label the ester on the right in blue, and I'm going to label the ester on the left in orange. Can you tell me which ester, blue or orange, becomes the ketone? No? Use that methyl group as a marker. The methyl group is on the alpha carbon of one ester, but not on the alpha carbon of the other. Which ester becomes the ketone? That orange ester. We know the orange ester becomes the ketone, meaning we know the orange ester is the one that gets attacked, opened, and then goes through elimination, because its alpha carbon has a methyl group, and its alpha carbon still has a methyl group. So why did this form and not this? What you can see in this product, that methyl group, that methyl group still helps us track our two esters. So now I can see it's the blue ester that becomes the ketone, and it's the orange ester that's served as the nucleophile. So the question that I want to consider is, why did we produce this structural isomer and not this structural isomer? And I'm going to take us to this part of the mechanism, that fourth step where we make an enolate. Let's say the product that we form is A, the product that we do not form is B. Compound A at step 4 Compound A has that alpha hydrogen. Compound A gets deprotonated at step 4. Compound A is now this negatively charged structure. But compound B, the structure that we did not form, what? What do you see? There's no alpha hydrogen. It can't be deprotonated. If it can't be deprotonated, that means it's actually still possible for it to react backwards. what that means is instead of the alkoxide forming an enolate by deprotonation, the alkoxide might instead reverse the process and start undoing this entire condensation reaction. What that looks like in terms of an energy diagram, we've got two different possibilities. One of them, A, forms this very stable, unreactive enolate. It's not going to be attacked. It's not going to be undone. Whereas B, when B forms, it actually sits at this higher place where it can have its reaction undone. What we describe this as is a thermodynamic well. The reason that this structural isomer forms is because there is an enolate that can form at the end of it, which makes it very hard to undo the reaction. Once that enolate has formed, it's game over. That's the product. Whereas this compound can't form an enolate, sits at an elevated energy, and can be undone. The reaction equilibrium can reverse it. So why do we form one structural isomer over the other? Thermodynamic wells. Why do we need this protonation step? Why do we need this acid workup? Thermodynamic wells. Okay. I have essentially 3 reactions left to give you. So we're on that second page front side. We're looking at Michael addition and Robinson annulation. I'm going to start by talking about conjugate addition. What do you think conjugate is trying to infer here? And feel free to leverage what you already see on the sheet. What do you think it's trying to infer here? I like this name because it's not named after a dead guy, so you can actually infer something about the reaction. That'd be nice, right? But it's not inferring conjugate acid, conjugate base. Good connection.
Is it the starting material is conjugated?
It is. We call that starting material what? What functional group, I mean? Conjugated carbonyl. Or an alpha beta unsaturated carbonyl, but calling it a conjugated carbonyl is what explains why we call this conjugate addition. So a conjugated carbonyl reacts with a mild nucleophile to go through conjugate addition. This mild nucleophile attacks at the beta position. And I'll demonstrate quickly why it attacks at the beta position. We know that there is of course, a partial positive on the carbonyl carbon, but resonance demonstrates that there's also a partial positive on the beta carbon. So a nucleophile could attack at either of these positions. Why would a nucleophile prefer to attack beta versus carbonyl? Well, we already know about things that attack at carbonyls. So what if we talk about an organometallic like an organolithium or a Grignard? These we know run acyl addition. Despite the fact that they could attack at the beta carbon, they only attack at the carbonyl. If we attack at the beta carbon, though, and this is what happens when we use something more moderate, like an a lithium organocuprate. Cuprates are not the same type of nucleophile as our other organometallics. Well, look at that. There's resonance. Why does a moderate nucleophile attack at the beta position? The product is resonance stabilized. It's easier to form that intermediate. The top product, if it attacks at the carbonyl carbon, no resonance stabilization. The nucleophile has to be strong enough to open the carbonyl and not be stabilized by resonance. But the bottom position, you attack at the beta carbon, you form an enolate, and so you get this resonance stabilization. It's easier to do. There is a stronger partial positive at the carbonyl carbon because it's directly bonded to oxygen, so it's got that strong dipole. There is a stronger partial positive, so strong nucleophiles are drawn to that strong partial positive. But there's no resonance. This has a weaker partial positive at the beta position, but it's stabilized by resonance, so it's easier to form it. Conjugate addition. Also sometimes referred to as 1,4 addition. Now, under conjugate addition is a reaction called Michael addition. This is conjugate addition when the nucleophile is an enolate. That's the difference. Michael named the reaction after himself if and only if the nucleophile is an enolate. If the nucleophile is some other reagent, it's just conjugate addition. If the nucleophile is an enolate, it's Michael addition. So I gave you guys this on the sheet, the the nucleophile I gave you is acetone with LDA, which remember is the same as just saying negatively charged alpha carbon, enolate. What functional group does that form? When the alpha carbon of one carbonyl bonds to the beta carbon of a different carbonyl. Do you remember what I encouraged you to identify this as?
Like a
Shared beta. The structure of Michael addition product is a shared beta dicarbonyl. That's the only way that I can help you predict what the structure is going to be. Make sure that both of your carbonyls share a beta carbon. Doesn't it make sense? A nucleophilic alpha attacks the beta position, meaning alpha now has a new beta that is already beta to another carbonyl. When you are looking for the Michael addition reaction, you are just looking for shared beta dicarbonyl product. And our last one is the Robinson annulation. And I wonder if you know what annulation means. I'll be honest, I don't think annulation is a part of my lexicon except for this reaction. I don't think so. I don't think that it's related to annulment. I could be wrong. If I misunderstand what this word means and what annulment means, I could be wrong, but I don't think it's related. It means ring forming. This annulation forms a ring. So listen, Michael was bold for saying, if conjugate addition uses an enolate, name it after me. Robinson was even more bold because Robinson said, if the reaction is a Michael addition followed by an intramolecular aldol condensation, call it after me. The Robinson annulation is two reactions in a trench coat. The Robinson annulation is a Michael addition that is followed by an intramolecular, and we know intramolecular reactions form rings. Look at the Deichmann condensation. An intramolecular Claisen forms a ring. Oh, this is the Deichmann. We're literally looking at it. Forms a ring. So the Robinson annulation is the same way. If the Michael addition allows for this possibility of an aldol condensation, then the aldol condensation occurs. So I gave this on the sheet, and it forms the Michael addition product. It forms that shared beta dicarbonyl. And if this is introduced, I think this is where I messed up. So I've got a blank arrow, and I messed up. That blank arrow along the top right, we will need some extra hydroxide. We will need some base to catalyze this intramolecular aldol condensation. So how does that work? Well, we've got a base So one of our carbonyls becomes an enolate. And when that enolate forms, it can intramolecularly attack the other carbonyl carbon. 1, 2, 3, 4, 5, 6-membered ring is formed. You know I like to map my carbons, and I like to map them through the nucleophilic attack. Alpha carbon attacks carbonyl, 3, 4, 5, 6. Alpha carbon attacks carbonyl, 3, 4, 5, 6. Carbon 1 has just attacked carbon 2. Carbon 2 has a methyl group, and now this O-. And then, by that same mechanism that we saw earlier, the O- becomes an alcohol, and then another enolate forms before the alcohol is eliminated, and we get our intramolecular aldol condensation. Those are all the reactions I have for you this semester. And against all odds, we finished a week early. Which means that you now have 2 weeks to review for the final. Your final exam is 2 weeks from today. I'll be posting answer keys to the retrosynthesis and to the row maps. I also am hoping to clean up another roadmap worksheet for this unit. I've been told that Unit 5, these reactions, can feel the hardest to master, or not even master, but identify the processes. So some roadmaps I think will help you practice applying the reagents and showing the syntheses. It's been a great semester. Thank you guys for putting up with OChem 2 at 8 a.m. Anytime. I'll be here next summer. But I hope you guys aren't. That's my goal with this class, is that you get through it. You get the grade you need, and you get on to doing bigger and better things. And if, against all odds, you find a calling to teach organic chemistry, come talk to me. I'll talk you out of it. We've got 5 minutes left. What questions can I answer?
These reactions are doozies, aren't they?
They're weird. But time and time again, if you can predict the functional group that's going to form, it's super easy. But that means not just looking at it and saying, it forms a ketone and an aldehyde. Yes, it does form a ketone and an aldehyde. That's not enough, though. This is that shared beta dicarbonyl. That is important. It gives you specific structural connection between the two groups. Yeah.
I think it'll take practice, but I'll get it.
You've got time.
Yeah, I'm gonna practice a lot for this.
Good.
In last unit, for sure.
Let's imagine I wasn't leaving and that we had all of next week. Yes, maybe we would have gone through this a little bit slower, but we still would have had time next week for practice. So take advantage of that. Oh, I erased it, but I didn't actually ask you guys. Maybe I'll send an email. I don't know if I'll get a lot of replies. the STEM Center is hoping to do a review session for OChem 2. They even offered so much as 2 review sessions, a morning review session and an evening review session. And those review sessions could be next week, or they could be the week of the final exam. Do you have any sort of preference about first week or second week?
I feel like I'll just watch your OChem 2 review from last year.
Yeah.
Or for last semester.
Probably no plan on going to a review session held by the tutors.
Probably not, since I live far.
That's fair. Absolutely. Then I'll send an email to the class. If I don't get any hits, I'll just tell them to plan for themselves, whatever fits in their schedules. They'll get paid whether anybody shows up or not.
Are they going to plan for like this time period?
So the STEM Center opens at 9, and there's a tutor on Tuesdays at 9 o'clock that could help. I did poll the class. Was that this week Tuesday? I asked if I got a sub to come in, would people still come to class? And the majority said no. So I would recommend, if you still want to come during the class time, go to the STEM Center. And there's usually an OChem tutor that is there and able to help. There's also very few people that can sub for OChem 2 and be helpful in that. And one of them teaches at 5:30 p.m. So I'm not sure that I can get them to come in at 8 a.m. The other doesn't like to come in at 8 a.m. and straight up said that. So I had a hard time finding a replacement. I'm not sure that anyone was going to take advantage of them either. So this actually makes me feel like I am doing a bad job by not getting you guys a sub. But I just don't think that it would be as well utilized as maybe the STEM Center. I think the STEM Center would be a great resource.
No hate on my last professor, but I don't think she would teach the mechanisms as well, because she's PowerPoint.
Yeah. That's one thing. I just had an instructor the other day that was like, oh, can I see your PowerPoint slides that you use in class? No, you can't. I don't have any. Which I wonder how you guys feel about that. The worksheets do well enough substituting for a PowerPoint, don't they? Okay.
Yeah, because I was in her OChem 1 last semester, and we had sheets in class with questions that we'd go over, and then we'd learn from the PowerPoint, and she'd like show us the reactions. I feel like this is a lot better.
There is a benefit, I think, of seeing a big snapshot and seeing it done all at once. But any textbook can give you that. And there's so many like those PowerPoint slides you can find on the internet. There are places that publish them. So that's where I feel like I've got to give you something that a textbook can't give you. And that's the slow step-by-step process. So I hope you guys do leverage resources like that. I don't think that that's what I can bring to you that's beneficial. Before I ever taught OChem 2, I saw another one of our faculty teaching it, and just sat right up at the front of the class, pushing buttons on the laptop and just pointing at the projector and saying stuff and then moving on. I'd get bored. I don't know, like that to me is just not an engaging way to spend 2 hours.
Yeah, and then she's also, isn't she like a synthetic chemist too?
Who?
Natalie Delmain.
Yeah, a true organic chemist.
Yeah, so synthesis with her, she's like so good at synthesis.
Yes.
So it was tough.
Good morning.
Good morning.
Yeah, that's true. I think that's actually where I maybe lack a little bit, is I don't understand the application of all of these reactions as well as a full-fledged organic chemist. So I look at these and I know how they work and why they work. I don't necessarily know why they're used and why they're taught, because I've never had to use them. All right, guys. Good luck. You're going to do great. No. I'm going to keep the test here. I should email you guys, though, because if there's a conflict, if someone can't, then I'll arrange for it to go to the testing center. I actually am going to have Natalie sit for the exam and grade the exams. So it's easy. It's easiest. Yes. Yeah, I got very lucky. It's easiest if everybody comes here because then she's got everyone's exams.